Hello, I'm Chris. I'm a KMP developer. I'm continuing the series on how to program from the ground up, and we're going to be looking at the relays, which are so cool. We left off on the relays, how they worked, and I call them the Rockets relays because they're so loud when they go off. So the big idea is that we can use an electric magnet to control a switch or multiple switches. And the big thing is we could now use this thing to create a knot, the Boolean knot. So if the switch is on, whatever switch is, the relay is controlling can be off, and if the switch is off, the whatever the relay is controlling, whatever that switch is, can be on. So that's the inversion thing. So I'll doing that. Let's look at how this works here with a video example.
We have three basic logic gates, and they are AND, OR, and NOT. AND gate, it allows output current be high only when all the input currents are high. Output of one gate is low if at least one input is low. Let's see the simple two-input AND gate. When we connect two relays in series as shown, then it behaves as AND gate and allows.
Right. So you got these two things. When they're energized, it'll pull the switches. They're spring loaded here. Boop. Pull them close to this magnet, electromagnet, and when both of them are on, that means the and is the true. So that's what that is. So let's go ahead and keep going.
Output current be high only when both the inputs are high, otherwise it outputs low. OR gate, it allows output current be high if at least one of the input currents are high. It makes output current be low when all the input currents are low. When we connect two relays in parallel as shown, then it behaves as OR gate.
Parallel. It's okay. Yeah, here's the OR gate. Either one of these things are on, that's going to be true. So this is how we're doing it with the relays. Just pulling that switch over, and that's...
And allows output
make a whole computer.
If at least one input is high. Otherwise it outputs low. NOT gate, it just flips the input and gives the output. It makes output current high when the input current is low, and makes output current low when the input current is high. NOT gate is just a normally closed relay, and its output is just the negation of input.
So for me, I just play with this stuff, but just to see how this works, this is it. This is all we're talking about. We're not talking about some other magical place. The only thing we're doing is this. We're using this magnet to throw another switch or open a switch. That's all we're using it for. That's it. So you can do some amazing stuff with all that stuff. You can do.
Okay, here's the shortest loop on the relay computer.
So this is a computer that's built with all the relays in here. Now he has some programming logic down here that is used to upload and download the program, which I don't think the program is stored, but all all the calculations and everything like that is stored up here in these relays. So he's just using the relays to do all the actual operations of the computer, which we'll get into what they are, with just relays. And he's given the address here. He wants to start running the program, which he's set up someplace, and go.
Using 0 as a counter, and then jump to itself.
So I guess this is just the whole program right here. Maybe that's what that is, or he's just this is one instruction to or maybe I'm not sure what he has here, but this is the program that basically says loop and add 1. Go.
I'll have 0 on the display so you can watch the counter counting. There it goes.
You hear it tick 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 tick.
One count.
Those are all the switches on the electromagnet being thrown and open, on one side every cycle of the CPU, doing its calculation.
Per clock.
You can see where
so we can increase the frequency.
Where the lights are all, where the actual one of these relays is actually on. You can see it on and off. So he's got this thing all set up. It's pretty cool. This is one example. We'll show another one. So that right there is probably what 10 hertz, 20 hertz, 20 times a second, 10 times a second, 10, 15, 20, 30 times a second. Well, if you get 1,000 times a second is 1 hertz. So this is way slower than any other computers. But for the time when these things came out, this was how we started with digital computers. Let's check another one. Here's another one that's a little more complete. Like actual pure just relays. One relay, one. These are all relays, and all they are is a little electromagnetic with a switch on top. You can actually look inside the package. These little orange wires are the coils around it, and you can see where it just goes just a spring, and it's just nothing. It's real, and if they're closed up, you can't see the little things go up and down, but you can see them moving. And he's got the lights up here. You can see which ones are on or off. And he's just simulating a full computer here. And he's got the readouts here. Well, he's using some logic here, some TTL digital logic, but that's probably just to get signals in and out of the thing and to control it. But all logic is still in the relays. It's so neat. I just think this stuff is crazy because it's just the amount of effort to go into getting this to work is.
Here's my two relays. In this diagram, you can see the schematic here. We have.
So he's just showing it.
Actually,
showing the schematic for all the different relays. And this one has got one ground, and then it's going to go normally open, normally closed, normally open, and it'll switch back and forth between them every time that the magnet goes off. And I think he goes into some detail about how that stuff has all worked here. And then here's his
last two relays up here.
So here's the relays, and there's the diodes that are on the schematic. He goes into details of how they're all plugged together. And this does a relay memory. So this does a memory circuit. So you can see how that's all put together, and it just uses
it's there, which is going to drive it low, one data bus line. So
these are all can be simulated using relays or tubes or transistors. And then, these are the biggest things. The tubes get smaller, and then the transistors go down to, molecule size. And here's the hexadecimal calculator. I just want to show these because it just shows that this.
Okay, this is my hexadecimal relay calculator.
That you can do a complete system in these relays, and people did. But right about the time when the relays were getting good, the tube thing took off. So they were like, screw these relays, because it is pretty slow and they aren't very power hungry. And the transistors go, the tubes went like 1,000 times faster than this stuff. So
much more decimal. So
we can watch it go.
So A is 10, B is 11, C is 12, D is 4 bits. Like in green, this is 2 plus operator the math on, and we need to.
He's talking about the different pieces. You can listen to the video. He goes through the different pieces and shows how it all works and put together. It's pretty clever, and he does the whole project from beginning to end. You can watch it and see how it works. And here's another relay computer.
Both the binary relay calculator and the hexadecimal relay calculator.
And
have a normally closed pin.
Shows how he sets all this stuff up to do
of a gentleman. I'm pronouncing that.
Relay computers. So those are all full implementations of binary logic using simple electromagnets and relays. And
now that we have
just goes into a little more detail about how he built all this stuff together and some of the design mistakes he made, and
button, the LED still comes.
And shows why one of the problems with relays, they are not scalable. You can build a little demo computer, but going bigger than that, all kinds of problems, which he goes into here, what those problems are, which it's just like, ugh. So that's why they immediately, when the tube thing took off, when they realized, we can use these tubes, they were like, screw the relays, we're doing this now. And this animation is so nice. I'm so glad that someone did this, which is our U.S. government.
Electronic tube.
Here we go.
This is a diode, the typical 2-element electronic tube. Let's get inside it.
2 electrodes, a plate, and a cathode. So it's just got the top part, or the inner core and the outer core. Let's watch it.
In fundamental operation, it resembles an ordinary single-pole switch. A switch that can connect, for instance, this battery and its motor load. One power lead comes to the anode, the other lead goes to the cathode. When this switch is open, the contacts are insulated from each other by a vacuum.
So it should be connected here all electrically. So this thing right here is connected into this thing that goes into this thing, which is a motor, another electromagnetic thing. So that goes in the motor. They call that load. And then it goes in the battery to the plus, and then the negative side, and then it goes into this this side of the heating element, this little heating element thing, was just a light bulb, by the way.
By some inert gas inserted into an evacuated tube under low pressure.
Right, and this is a vacuum here, right, or inert gas. So there's no reaction. So there's nothing burning. This cathode cannot burn. That's why it goes on so long. But eventually it does burn. That's why these things were such a pain and very power hungry, because it's like having all these light bulbs on.
To close this switch electronically, all we need to do is heat the cathode.
So those are little electrons flying off when you turn this. So this battery here is all this is doing is like a light bulb. It's like the first thing we saw. That's all this was. So this is just humans messing with this stuff and finding out these different characteristics. So he heats up the light bulb. These electrons fly off, and when this thing gets charged, boom! When this gets connected up here, these will actually flow through this way. They'll flow this way. Boop, up this way. Around again, up this way. So it's got two different paths.
As electrons are emitted from the surface of the heated cathode, being negatively charged, they fly at tremendous speed to the anode.
Isn't it? This is actually really what's going. When you look, it's invisible. You can't see it, but this is what's going on.
In this way, a current-carrying path is formed, which closes our electronic switch and permits our motor to operate. You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus.
Okay, yeah. Okay, so that's the thing. It totally messes so many people up. It messed me up. The actual electrons are flowing this way, right? They're flowing from the negative to the positive, right? But when electrical people talk about it, they talk about it as if it goes from the positive to the negative. It's super confusing. Just know the actual electrons are always flowing from the negative to the positive, but in their schematic, they have it flipped the other way. And when people talk about it, this was one of those things. It was like, when I first discovered it, I was like, why are you putting us through this? Why are you doing this? It's like, this is how things have been forever. All the documentation's this way. Everyone that comes into this and knows is introduced properly is told this. So we just hope that you can figure it out. I was not introduced to this. I started messing with computers and electronics when I was 7 years old. Nobody told me any of this stuff. This was never told. I think it was in one sentence somewhere, and I just didn't understand what the hell they were talking about. I just looked at the schematics and just started rigging things together. Didn't really know what was going on, but it gave me a really good intuitive feeling of how this stuff works.
In the first place, we can rectify current with it, converting AC to DC. We can do this merely by connecting an electronic tube.
Okay, so just talking about how that works with AC, but we're not interested in that part. We just want to show you how the tubes work. And so with this, when they apply current to this thing, it's mean it'll control it on and off, on and off, on and off, on and off. Wait, let me see if did they power that part of it? Let me see if they have that part where they show the gate. So that's that. That's that. Okay, the grid. Yeah. So here's the grid.
Between the cathode and the anode of the two-element tube, which we diagrammed a while ago, we now place a grid. To this grid, we connect an input of some weak voltage.
Grid is just another piece of metal. The same stuff this is made out of here, the same metal it's made out of here. Same little metal. It's just a little mesh that is supposed to act as like a gate. It looks like a little grid. It actually looks like a grid or whatever. It's just it's trying to block it. So it's either gonna let stuff go. It's gonna let stuff go through, or it's gonna block it, depending on how it's charged. That's it.
We wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens.
Electrical, yeah.
Every time a negative potential is impressed on the grid, even though it be very minute, it has a large effect in reducing the number of the negatively charged electrons which would otherwise keep flying from cathode to anode.
Right, so just a tiny charge makes it stop. It has to be negatively charged for it to go up, or the tiniest amount makes it stop. And Just that. This is just something we discovered as humans about electricity, how it behaves in a vacuum. We didn't really know this until we had the ability to actually create vacuums. Until we were able to put gas, to create a vacuum, and then some people had enough time to mess with this stuff, with creating a battery and having a vacuum and having these, and had to be like glass blowers because they had to make these things with these wires in them. It took forever. It took forever.
Conversely, when the grid is positive, an equally large effect is exerted in...
Oh, yeah, I got it wrong. So I got to see it's so easy to get it wrong. So it's like when you charge it positively, I just forget which one it is. It allows it to, because it's attractive. So these negatives are attracted to the positive grid that attract to this one. But when it goes negative, their like charges oppose each other. So so they totally like don't get near me at all. So electricity is just odd. It's just this is how it behaves.
Increase
It doesn't know it's negative or positive. It's just doing its thing.
the flow of electrons from...
We call it negative. We call it positive. It could be George and Larry. George is going one way, Larry. If there's two Larrys in the room, they're not going to be together. But if it's a George and Larry, they hang out. It's just humans like anthropomorphizing our ideas on nature. Nature's just doing its thing. We have just call it this. These are just discoveries, and they only happened like a couple hundred years ago. It's like, what?
Cathode to anode.
Stumbling around this, like the journey of all this computing stuff is just stumbling around, figuring out stuff that works, and then it's trying to scale it up and seeing what works and what doesn't work. It's so much of that junk, and that's why it's like, why can't we get it right? It's like we haven't been getting it right the whole time. We've been just messing with one thing after another, trying to get this going, making our jobs easier.
Here is this. A small amount of power applied at the grid is amplified into a large amount of power in the anode or work circuit. This amplified...
Right, so this is the power that lake, right? This is the power source that drives the whole thing. And this is the control, whether it's the gate is open or not. There's a thing. This is what drives it open or close. This is the thing that opens up the gate or not, and this is the thing that we want to have controlled, whether it's an on or off, with zip. If it's a 1 or 0, that's all we care about with computing. They can also do all kinds of other stuff with these tubes, just like we can with transistors. But this is the only thing we're using it for in computing is whether it's on or off, and all this other behavior, whether it's kind of on. No, we had to train to eliminate that stuff as much as possible. So that's why there's a time step that allows things to fill up and deplete and change state, because there's a time involved with this stuff. Until we get that problem fixed out, there's always going to be a time factor involved. The only thing we've made it says we make it smaller and smaller and smaller until it's so the speeds when you make this is really small, makes it go a lot faster. That was the whole thing. So I talk about some of these things, which I just mentioned. These are just some notes for you. So here, let's see what this one. Is this the one I just opened?
Nearly all vacuum tubes operate under just a few fundamental principles, chief among which is thermionic emission, which is the phenomenon that when something with a negative charge is heated up, it tends to emit electrons. In a vacuum,
tends to emit, yes. There's those X ones around, like if you used to, if you hook up another source, it'll use it just like it's a wire,
tube, there is a filament inside a glass tube that has been pulled to a vacuum. If a separate negative charge is applied to that filament, the filament will start emitting electrons once it gets hot. If an additional plate is placed inside the glass tube and given a positive charge, the electrons will be attracted to it. However, since heat...
Well, and this will also work outside of a glass tube. It's just the wire heats up too fast to get any kind of power coming out of it. So that we kind of knew that this was occurring, but until we put a vacuum, until someone's like, what if we put a vac? What if we put nothing in there and see if it doesn't burn? It's like, oh, that works.
Heat is required to emit electrons. If the charges are switched, no electrons will flow. This creates a one-way valve for electrons, otherwise known as a diode. Here you can see a 5642 directly heated diode.
You can see it right there. There's where all the electrons are coming from, and they're hitting this little. This is the anode, and this one's the anode. But in the case of other ones, it'll be the grid, the control grid, and the anode will be someplace else, like around it. and this will have more holes in it. But this is just a diode one way.
Being used to light an LED. When the charge is reversed, the second LED would light up if the diode wasn't doing its job. But as you can see, the second LED isn't lighting up, which means that the diode is only allowing electron flow in one direction.
Right, so that little LED is just being used as an indicator light. That's all it's putting on there. All right, let's go see what this one's about. This is so cool. Very useful to know this because transistors do the same kind of stuff, just a different way.
To modern high-power transmission with its great water-cooled tube, radio has shown constant progress. Sturdy, efficient tubes make possible our modern military sets. These tubes serve in both receiving and transmitting installations. High above the earth,
yeah.
using current flow. When constantly in motion.
Here.
A conductor contains a relatively large number of free electrons, all of which are constantly in motion. When a voltage is applied, the electrons are forced through a conductor, producing current flow. The movement of free electrons in a conductor may be accelerated by the application of heat to the substance of which they are a part. If the temperature of a metal is increased enough to cause the metal to glow, some electrons will gain enough momentum to cause them to break away from the metal.
Right, so we kind of knew that heating stuff up made electrons pop off it, because we could also see the photons popping off it too, because it's glowing, right?
They return, however, due to molecular attraction. In many radio tubes, the same action takes place when a filament is heated by a current of electricity. In the open filament type of tube, when the wire filament begins to glow, it gives off a cloud of electrons. They swarm about the filament, leaving it and returning to it at high velocity. Although pictured here, electrons actually are invisible. Many modern tubes have an indirectly heated source of electrons. The heater, made of tungsten wire, is surrounded by a thin metal sleeve. This sleeve, or cathode, is coated with oxides of barium and strontium. When heated, it becomes the source of electrons in the tube. Here we see the cathode of a tube after the glass bulb and other elements have been removed. This oxide-coated sleeve, or cathode, contains the heating element inside. The heater is insulated from the sleeve. The heated cathode, with its swarm of electrons, is surrounded by a larger tube element called the plate. These two parts, the cathode and the plate, are the principal elements of the diode tube. All tubes contain these two essential elements.
So I'll let you watch the rest of that. Super interesting how these things are built. This is a really great explanation of the switching.
The triode's construction is very similar to
The switch. So this is where the diode. Now we got the triode. So the diode has just two. And only, it's like one way. One allows electricity to only go from negative to positive. Only one way, or negative, positive, negative. It only goes one way. With this one, it has this little grid. You can see why they call it a grid. It's because it's got this little wire, this little wrapped wire thing inside here, or here. I can't. And whichever one. I think this is the cathode. And yeah, so I don't know which one it is. He'll explain it here in a second. But the electrons fly off one and go to the other, and this thing controls whether the grid says whether you get to go or not. So that's like the external switch on the relay. It's like this thing. It's like the grid. This thing right here is like this thing. It's just controlling whether that other main current gets to flow or not. Yeah. So let's see here. Where am I at?
The triode's construction is very similar to an indirectly heated diode. There is a filament that heats up a negatively charged cathode, and there is a positively charged plate. The triode features one additional element in between the cathode and the plate, the grid. The hot cathode emits electrons, which are attracted to the plate, but the flow of electrons to the plate can be controlled by the charge on the grid. If the grid has a sufficiently negative charge...
So I guess the more modern design is they've got the heating element, which is light bulb, and they actually just hooked it up to this plate thing to make it more of a flat, so they have more surface area for electrons to fly off, but it's all just connected together. So they call it the plate and the filament, and they're the same thing, man. It's the same stuff. It's like, if this plate thing wasn't here, these things would be coming off just less, right? So that's just they improve the efficiency a little bit. Say, hey, if we do this flat thing here, it'll give off more. I'm like, okay.
No electrons flow. If the grid charge is brought more and more positive, more and more electrons flow. The very high voltage on the plate, which can be anywhere from 24 volts to 300 volts and more, can be controlled with a very small voltage on the grid, often between negative.
Right, here's the grid, the control. That's that control stuff. Whether it's on or off, but it can put massive current across here. This could be like tiny current. This could be massive current across here. You can have like a huge water cooled radio transmitters. The amplifiers, these things, these things are gonna get super hot with like massive amounts of electrons going across that. It's gonna get super hot.
10 volts and 5 volts. Here you can see a 6DJ8 dual triode changing the brightness of an LED in accordance with the input on the grid. This graph very clearly shows the relationship between output voltage and grid voltage for an inverting amplifier triode. As the grid voltage increases, more and more electrons flow, bringing the plate potential lower.
Okay, so that's how it works. And let's see, this is some vacuum tube NAND and NOR gates. Let me see if I can go. This is the same guy. He's so cool. He just does all these great experiments and shows off how these things are built, which I'm not going to go. I mean, I'll play a little bit of it. I'm not sure. He builds up these circuits and shows you how they can make them with tubes, which is awesome. I mean, he shows you in detail the core elements of how all these tube computers work, which is great. And he sets that all up and shows you all that stuff. So I'll let you go watch that. And here is a nice overview of all these tube computers
and other
where they came from, how they're put together, and different computers. There's some more relays they're talking about. Here's that Williams Kilburn tube memory system. There's all the dots, sequence of dots. They're using them for RAM. They just used anything they can get their hands on. Here's like some early computers. Here's some people putting them together. Here's how they work. Here's some early radar tracking. Thought that the Ruskies were gonna kill us all. And this is all that same basic tube technology. Just amazing. 1950s, or 1957, 1955, somewhere in that range. This is when we discovered, like, hey, I think we need to have a computer language. I think we need a computer language to deal with all this complexity. We needed something to deal with all. We can't just make tubes for all this stuff. It's too much. It's too much. And the vacuum tube is voracious because it consumes a lot of power. Excess heat to the cathode. Yeah, it's just really bad. So that's at the half-hour point. Yeah, I'll come to the next one with the transistor. Yes, we'll do the transistors next. That's what blew the doors off all this stuff.